All right, ladies and gentlemen, class recording started. So, yesterday, we talked about these 4 situations where this crate was under the influence of a number of forces. And in the first 3 examples, section 1, section 2, and section 3, or number 1, number 2, and number 3, the crate was constantly in equilibrium. Sometimes it was not moving in equilibrium, and sometimes it was moving with a constant velocity in equilibrium, right? But always equilibrium. And the key point of being in equilibrium, whether it's at rest or whether it's moving constant velocity, is what has to be true?
Net force is 0.
Net force 0, right? So all those forces balance. Not until we got to number 4, where we got a force greater than friction F, right? Now greater than friction F, now we have a net force, now we experience some acceleration, okay? Are we okay with that idea? This part, especially the first 2 sections, leads us to a discussion about friction, okay? I think we've probably, we're aware of friction, we're aware of it, that it exists, but what it can do and how it affects certain situations sometimes isn't quite to where that's where we have to look at it a little bit closer. So, that being said, let's go here. Nope, not what I wanted to do. For that. Okay. All right. So first, net force. Okay. This discussion about friction starts with net force, which doesn't show up on your outline, but just to review. What is the net force on an object? Eris? The total amount of force, or the combined effect of more than one force, right? Mathematically, Eris, how do we figure out the net force?
Well, if there's 2 acting opposite directions, you cancel out.
Mathematically, what are we doing to those forces? Summing them, right? We are adding them, right? The net force is the sum of all the forces. But because forces are vectors, if one's in one direction and one's the other direction, one's going to be positive, one's going to be negative, we end up subtracting, but really we're adding, right? We're just adding negative numbers sometimes, right? We're good with that, right? But the one thing we talked about is, and you guys found this out on your quiz that you guys took. Did you guys get your quizzes back, by the way? All right, hold on one second. I'm going to pause this. And I want you guys to get your quizzes that you took on Thursday, because I graded them. I want you to get them out of the All right, ladies and gentlemen, we are back. So, as you found out on your quiz, right, the net force acting on an object, the combined effect of all of the forces that are acting on that object, is what we look at to determine what's going to happen to it. Does it accelerate? Is it in equilibrium? Is it at rest? Is it moving with a constant velocity? All these things that we could consider about it. Is it speeding up? Is it slowing down? Is it changing direction? We have to look at the net force, or the combined effect of all the forces. Okay? Good there. All right. Let's go on then, and let's talk about one force that we encounter quite a bit that plays a big role in all the things that we do here on Earth. And that force is friction. So, by definition, friction is a contact force that opposes the motion of an object, or we will find out it can oppose another force if there is no motion. So friction is always an opposing force, meaning, right, Eris, if friction is always an opposing force, when we look at examining it in a problem or something, it's generally going to show up as what? Negative, right? Not always, depending on the situation and depending on how we decide what's positive and negative, but generally it's going to show up as a negative force. Okay? So friction is a contact force that opposes motion. Contact force, right? Has to be, surfaces have to touch in order for there to be friction. If there's no contact, there's no friction. Okay? And then it has to oppose something. It has to oppose motion, it has to oppose another force. It's a negative force. It's an opposing force, but it has to oppose something. And we'll talk about those situations more as we go along here. Okay? All right, so let's talk about this picture here. So, this guy buys himself the flexorciser, all right? And we'll see why. You'll see here in a second that he probably needs it, okay? Apparently, he doesn't have, well, the company that he bought the flexorciser from apparently doesn't do in-home delivery, and just dropped it off like in his driveway, apparently, right? And he doesn't have a dolly, so the next best thing, let's just lasso that bad boy and let's just drag it into the house, right? That's obviously the next best option, okay? So, as you might expect from somebody who is purchasing a flexorciser, right? He applies a force to this box. He has expert lassoing skills, apparently, but applies a force to this box, but nothing happens. Right? Now, the standard response to that most people would give in this situation is, oh, he pulls on the box but nothing happens. Why? And a lot of people might say what? He's not pulling hard enough, or
Friction.
Most people wouldn't say that. Most people would say it's too heavy, right? That's what most people would say. But too heavy is implying about what like factor about the box? The mass. Mass doesn't determine if something accelerates. What does mass determine?
How much it accelerates?
How much something accelerates. You, by yourself, could move an entire planet. We'll talk about that more on Friday. All right? Mass doesn't determine if something accelerates. Mass determines how much something accelerates. What determines if something accelerates? How did this discussion start?
Net force?
Net force determines if something accelerates. So here, the correct answer to this question would be, if the man applies a force to the box but it doesn't move, what has to be the case? That's inertia too high means that it's too heavy, and that's not why it's not moving.
Friction's equal to the forces applied.
Let's go with more generically, there has to be another force on this box, right? Eris, which direction does that other force have to be?
The opposite direction that he's pulling.
Opposite direction that he's pulling, how big does it have to be? Equal. Not bigger, equal. If the force, right, if this is his force and he's pulling this way, right, and there was another force in the other direction, right, Eris, if it was bigger than, if blue was bigger than red, what would happen?
And we get pulled.
The man would get pulled in the left direction, and that doesn't happen either, right? Okay? So, in this case here, right, the man applies a force to the box, but the box doesn't move.
So if you were to apply less of a force to friction, the force of friction would change.
Yes. Good. You're jumping ahead. That's okay. All right, so if the box doesn't move, that means that the net force on the box has to be 0 and no motion occurs. And in order for the net force to be 0, those two forces have to be equal, right? So, Andy, kind of jumping ahead, but let's go the other direction, okay? If the guy pulls on the box and nothing happens, his next response is then to do what?
Pull harder.
Pull harder. Right? No, we kind of talked about this, right? If the net force on the box is 0, there has to be another force acting on that box. How big does it have to be, Eris? Equal and in the opposite direction. So that when we add them together, we end up with 0. Right? So then, right? Must be exactly the same magnitude as the man's pull, but in the opposite direction, so they add up to 0, and net force is 0. Okay? Good there. This is all kind of review stuff. We'll get to the actual information in a second. All right, so, Andy, right? Oh, sorry. We'll get to that in a second. All right. That force that is acting on the box we refer to as static friction. If we refer to something as static, what does that mean? Constant or not changing, Nick, right? Remaining the same. Static friction is a frictional force that prevents things from moving when a force is applied to it. Things don't stay still because they are too heavy. Things stay still because there is a frictional force acting on them in the opposite direction of the way that you are pushing that balances out your force and makes the net force 0. Okay. Good there. Andy, now I think the next slide, right? So, his response to that being, he pulls harder. He pulls harder, but the flexorciser still does not move, right? So he went from pulling this hard, right, to now pulling this hard, right? That being the case, what had to have happened?
The force of friction increased.
The force of friction increased as well. How much did it increase to, Andy?
Equal to negative amount.
Equal to his pull, but a negative amount. Meaning, what can we then make a connection and deduce about static friction? What did you say before about the frictional force?
It changes.
It changes, right? Man pulls harder, but nothing happens. Why? Because static friction is not a constant force. FSF, force of static friction, right? We use the subscripts to signify which force we're talking about, right? A lot of times we'll use F to represent force, and then the subscript to represent what force we're talking about. So FSF, the force of static friction, changes with the applied force so that the net force remains 0. And if the net force remains 0, what's going to happen to that box? Nothing, right? It does not accelerate, does not change what it's doing. All right, good there. Okay, so let's take a look at this graph, I think. There we go, all right? Notice the first part of this graph down at the bottom is labeled as the static region. This graph, look at your two axes, right? The x-axis, what is the x-axis labeled as? Applied force. That's going to be what in our situation that we were just discussing? That's the man's pull, right? And then on the x or y-axis, sorry, we have a frictional force. In this static region, as applied force is getting bigger, the frictional force is also getting bigger. Right? Question. What's the slope of that line? The slope of that line has to be a specific number. Mark.
1.
Has to be 1. Why, Mark?
Because the applied force and the frictional force are not equal unless the slope is 1.
Right. If we apply a force of 3 newtons, how much frictional force does there have to be? 3 newtons. Right? If we apply 5 newtons of force, there's got to be 5 newtons. Right? It's always 1, 1, 2, 2, 3, 3, 4, 4 if we're looking at ordered pairs. Right? And that leads us to a slope of 1. Right? Those, as we go along up here, right, this whole section, the frictional force matches the applied force. And so we refer to that as the static region. Because during this part here, right, if frictional force is matching the applied force, what is the net force going to be? Well, what is the net force going to be? 0. And nothing will happen. Nothing will change. No acceleration. Okay? Good there. All right. You can see this from the graph, but also from personal experience. Can this happen indefinitely? Can static friction just keep matching applied force forever and ever and ever? No. Because if it could, what would we find?
Nothing.
Nothing would happen, right? Nothing would ever change. So there has to be a limit to what static friction can do. All right, so the guy in the flexorciser, he can't cut it, right? So he has to call in this hoss, right? Look at him with his hard hat. I mean, if you just wear a hard hat around, you know, you're just like, some people wear a baseball hat, you just wear a hard hat, you know, you mean business, right? So, this guy comes in, and he applies a big, huge force to the box, and it starts to move. Why? His force is greater than the frictional force, right? So his force, right, if it moves, that means that there's a net force acting on the box, and it will accelerate. In this case, it will speed up. Static friction can only increase to a certain amount. We refer to that amount as the maximum static friction. Once you get past the maximum static friction value, you will apply a bigger force than the maximum static friction, so now there's a greater force one way than the other, and that results in acceleration. Right? That value that we're looking at we call the maximum static friction. I think there's some over here. Right? Oh, okay. So in this case here, in order to get this object to move, we have to apply a force that is greater than the maximum static friction value. Static friction will increase to a certain amount, depending on the surfaces that are involved, right? Are we talking about surfaces that are rough and have a lot of friction, or smooth, right? But also depending on the mass of that object. Those things will affect, it's actually not the mass, it sort of indirectly is the mass, but how big the object is does affect how much static friction it has. I won't hold you guys responsible for that right now, but just know that it does. Okay? All right, good there. So, we see here from this graph, right, in the static region, it continues to go up, 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 meaning that frictional force is matching our applied force until we get to this spot right here, right? Notice that spot on the y-axis is labeled as Fs max, right? The maximum static friction value. Perhaps you've experienced, though, this idea if you're like moving around, like you're rearranging your bedroom, and you're changing the furniture in your bedroom or your living room, right? And you like want to move your dresser. Your dresser is really heavy, right? It's hard to move. It doesn't move not because it's not too heavy, but because there's a lot of friction between the dresser and the carpet in your room, right? But if you can get it to start moving, usually it's easier to keep it moving, right? Harder to get it to start than it is to keep it going. Here, once we get past the maximum static friction value, what do you see happens to the y values on this graph?
Goes down.
They go down, right? And the y values are telling us about the frictional force. So once something starts moving, it experiences less friction. And also, what do you see about the frictional force that it experiences once it's already moving? It's constant. We refer to this as the kinetic region. Kinetic implies what? We talk about something being kinetic, that means that it's what? Moving, right? Or changing, right? We've run into kinetic energy already this year, right? Implying that it's motion, right? Once we reach the maximum static friction value, friction switches from static friction to kinetic friction, right? Kinetic friction is a frictional force that acts against a moving object in order to slow it down. Kinetic friction is generally what most people think of when we talk about friction. Like I said, in the first part, where something doesn't even move, most people are like, oh, it's too heavy. Not really. There's a frictional force acting on it, right? But most people think of kinetic friction, this frictional force that acts on a moving object. All right? Good there. So let's talk a little bit more about kinetic friction. Kinetic friction is always less than the maximum static friction value. Which means, like from your personal experience, right? Maximum static friction value is what you have to overcome to get something to start moving. But once it's already moving, it experiences less friction than it did to get it started in the first place. Kinetic friction is always less than the maximum static friction value. Right? Meaning that it's harder to start motion than it is to keep moving at a constant velocity. Okay? So if I take this book, right? So I can do this demo. I have tried to let my table loose. So, right? I push this book just a little bit. Nothing happens, right? I push a little harder, still nothing happens, right? But I give it a big shove, and that happens, right? So at the beginning, when I'm giving it the big shove, I overcome the maximum static friction value, so it starts moving. But what eventually happens to it? Slows down and eventually stops. So at the beginning, when I'm overcoming friction, positive acceleration is occurring. But as it's sliding across the table and slowing down, negative acceleration is occurring. Right? So what has to happen to it in order to get that negative acceleration to happen? Once the box is pushed, it slows down and it stops. Are the forces balanced as it's slowing down and stopping? If forces were balanced, what would it do? What? No. If the forces were balanced, what would it do? Keep moving how? Constant velocity, equilibrium, right? As it's slowing down, is it accelerating? Yeah. And if it's accelerating, are the forces balanced? No. There has to be a net force acting on it, right? Forces are not balanced. Slowing down is acceleration. So there has to be a net force that is not equal to 0. Right? That force that's acting on it is kinetic friction or sliding friction, depending on what book you read. Your book I think your book uses sliding friction because maybe you guys can't handle a big word like kinetic. So, but in the big people physics books we use kinetic friction. So I feel you guys can handle that. So, all right. Once the box is pushed, right? Once that book leaves my hand, the guy pushing the box and me pushing the book are exactly the same situation. Is there an applied force to it? No. In order for me to apply a force, Eris, what do I have to be doing to that book? Touching it. As soon as it leaves my hand, there's no force in the forward direction. Why does it keep moving in the forward direction then?
Because it's accelerating.
How is it accelerating?
It's slowing down.
Slowing down, right? But why does it keep moving forward as it's slowing down? Inertia, right? It was moving forward. It's going to try and keep moving forward as much as it can. But, right? Originally, let's go back here. Oh, there it is, right? So, forces. Big push forward, not as big of a force backward, right? Applied force greater than the maximum static friction. But once we get here, right, is there still a frictional force? Yeah. Acting in this direction. But is there a forwards force anymore? No. So if something's moving forward, but friction is pulling it back the other direction, what's it going to do? First it has to do what? First it has to slow down, right? And then it eventually stops. Okay? Once it stops, is the kinetic friction force still there?
No.
No. Do you know why, Eris, or are you just guessing?
Because kinetic friction only acts on moving objects.
Okay, so kinetic friction only acts on moving objects, right? But as this book is sliding across the table, right, the friction force is acting on it towards the board. Yes? Right? If an object stops, but it still had a force acting on it towards the board, what would it start doing? It would start going towards the board, right? Does that happen? Once it stops, right? So, kinetic friction only acts on moving objects. No movement, no kinetic friction. So this is a case, like we said at the beginning, friction has to oppose something, right? It doesn't oppose the force anymore because there is no more force, right? There's no applied force, but it does oppose the motion. It has to go against something. All right? Good there. Questions? All right, tomorrow we get into impulse momentum, Newton's third law, and conservation of momentum.